All right, what's up, guys? So, I know some of my classes are at different points in this unit. So, here's what I'm going to do. I'm going to start out. I'm going to go back over complex conjugate and dividing complex numbers in case you have not learned it yet. You can stop the video, rewind it, and watch it, and go back and forth as needed. But if we have already covered this and you feel like y'all got a good handle on it, just tell my sub to just fast forward this video to the part of completing the square. That's what your next lesson would be. So I'm going to go ahead and tackle this real quick and just do a little mini lesson, and then we'll get right into the completing the square. All right, so complex conjugates. So two complex numbers in the form where you have a plus bi and a minus bi. So just some things to remember. The a parts being the real numbers, the bi is the imaginary number. So basically, if the imaginary number is just a different sign, those are what's called complex conjugates. So what those are good for is, especially in a minute when we actually have to rationalize the denominator, this can be useful to remove that I from the denominator. If that doesn't make sense, don't worry, I'm going to explain that here in just a second. But that's just a quick overview of what they're useful for and what they do. I'm just going to do a real quick demo of how to multiply complex conjugates and what that looks like when you do that. So two binomials being multiplied. Remember the FOIL method, right? So that would give me 64 minus 8i plus 8i minus I squared. So you'll notice real quick, the middle terms, they're going to go away, leaving me 64 minus I squared. So after I look real close, look here, negative, and then you got an I squared. I'm going to be very cautious how I write that and make sure I put the negative 1 inside a parentheses, because I want to remember that I'm saying minus a negative 1 squared. So, I'm sorry, negative 1. Oh, Lord mercy. It's late in the afternoon, by the way, if you're not aware, so I'm having a dumb moment. I squared is negative 1. So for those of y'all who went, huh? Sorry, I'm very tired. So that's really 64 plus 1, which is 65. So what complex conjugates actually do when you multiply them is it removes the imaginary part. It becomes a real number. So that's just a very general overview of those. I would encourage you, if we've not done this yet, I would encourage you to stop the video, try number 12, and see if you can do it, and then we'll move on from there. So I'm going to pause it, and we're back. So this one, your final answer, I'll just go ahead and tell you. Your final answer should have been 41. So 25, 16, yeah, 41. Should have been 41. So dividing complex numbers. Here is some things to watch out for. So you cannot have an I in the denominator. To be real brief here, remember, I really represents the square root of negative 1, and we do not like square roots in the denominator. So that's the why we're doing that, is to get rid of the negative. I'm sorry, the square root in the denominator. So number 13 here. So I'll use this as my example. If I have a monomial in my denominator. Remember, mono prefix means one. So one term. What I'll do is I'll multiply both top and bottom by I. And then I'll just multiply straight across. That would give me 10i over 2i squared. So we go through and we're like, okay, 10i. Okay, now there's 2i squared, but we got to remember I squared is really negative 1. So it's 2 times a negative 1, which is going to give me 10i over negative 2. So before I circle this, move on, I want to make sure that these cannot be reduced. In this case, it actually can. 2 will go into both of these. They're going to 10, 5, and to itself once, leaving me a negative 5i. And you're done. That's it. I will try to leave an answer key. If I remember, I'll leave an answer key with my sub, so that like when if you're working the rest of these on this page out, you can go check them at a later time, or she can call the answers out, or whatever y'all work out. And you can check to see if you're right with these. So I'm going to move right along with what happens if you don't have a monomial. What if you have a binomial? What do you do? So I'll do 17. So have a binomial. Now remember, it's always the denominator. That's what I'm trying to get the I out of. I don't care. Now this one doesn't have one, but like 20 and 18 and 19, they have an I in the numerator. I don't care. That's fine. I just don't like the I in the denominator spot. So I'm going to do this one. I'll do this one, but I'm going to remove this. So I'm going to multiply by its complex conjugate, which is 5 plus I. Remember, basically, the imaginary part, you just change the sign. That's all you do. Okay, so so I multiply both top and the bottom. So when I multiply straight across, I've got negative 2 times 5 plus I. Okay, thing's still working. Yeah, that's good. All right, so distribute. Okay, so this I've got to FOIL it out. So that'd be 25 plus 5i minus 5i minus I squared. So, yeah, okay. So those cancel, they gone. So you got 25 minus I squared. So the I squared, remember, is negative 1. So I got to remember that's 25 minus a negative 1, which would really be 25 plus 1, which is 26. So all that gives me 26. Now, before I go off and just circle it and say I'm done, what I want to do is I want to make sure that there's no reducing that can take place here. And in this case, there is. So here's how I traditionally show how to read these, because people sometimes have trouble seeing that there's two fractions in this. I have two terms that are sharing, let's say, a common denominator. So I can rewrite this as two fractions that would look like this. Negative 10 over 26 minus, because of the minus right here, 2i over 26. See the 10, negative 10 and negative 2, they're still over 26. So these are equivalent expressions here. So I just now look at them individually and say, okay, 10 26ths. What can that reduce by? And I look and say, okay, well, 2 will go into both of them. 2 will go into 10. 5 times 2 will go into 26, 13. 2 will go into itself once. 2 will go into 26, 13 also. So when I got it reduced down, I just rewrite it. So that'd be a negative 5 over 13 minus 1 over 13. You're done. That's it. That's a perfectly acceptable answer. Sometimes you might see them, some people might elect to do this. Just put it back over the same denominator. That's okay too. Both of these are perfectly acceptable answers. So with the rest of these, those will be for you to try. Now I will say, like with these right here, what'll end up happening, like for 20, for instance, you'll you multiply both top and bottom, right? So you'll have some foiling that'll take place on the top. You'll be foiling on the bottom. That's okay. It's a lot of work, but it's not difficult. It just takes a minute to go through, okay? So I will leave that with y'all, and y'all have fun with that. All right, so we're back. So if you were already caught up on that previous little lesson earlier in the video, great. So what we're talking about today is using a method called completing the square. And we're using that method to find the roots of a quadratic. So this method, I needed to go through and show you just how you complete the square in general first before we actually go find the roots with it. So completing the square, here's what it means. It's, not all trinomials were able to be factored. Like for instance, let's use an example. Let me zoom in so I just got a little white space here. So if I had a trinomial, let's see. Plus 8x plus 16. This will work. So a trinomial that looks like this. If I went through and did the traditional factoring method, I'd find out real quick 4, 16. So my two binomials would be x plus 4 times x plus 4, which simply written would be x plus 4 quantity squared. So this right here is what's called a perfect square trinomial. We did some of these here a while back when we was doing special cases of factoring. This is what a perfect square looks like. Trinomial looks like. So these are special cases because they are not always happening. There's a special occurrence. But here's the good news is that I can actually force one of these to be a perfect square trinomial. I can force just about every one of them to be that. In fact, with just doing a little bit of manipulation of the equation. So here's how this works. So to complete the square, I'm going to have to rewrite this. The standard form is ax squared plus bx plus c equals 0, right? But your step 1 here is saying rewrite it where you basically move the c value over to the other side is what it's saying. Okay? So then, let's take a look at number 3 here. So number 3, I'm going to make that a little bit bigger here. Okay, there we go. So with this, hang on, let me make sure no glare anywhere here. No, you're good. All right. So first thing I'm going to do is I'm actually going to subtract 56. And then I'm going to rewrite it saying x squared minus 18x equals negative 56. Now notice, and this was not haphazard, I left a little space right here. This space is going to be filled with something. So here's the process from, so step 1 was rewriting it, which I've done. Now step 2 says divide by the a value. Now I'm lucky in this respect that the a value just happens to be 1. So if I divide everything by 1, it's still the same thing, right? So no new stuff there. So my third part, so I'll real quick just brief. So third part, it says complete square so it's telling you all the steps to go through. So here we go. Here's the process. I take this number. Now notice I'm circling the sign with it. So I'm going to take half of that number, and that's going to give me a negative 9. I'm going to take that negative 9, and I'm going to square it, which is going to give me 81. That 81 is going to go here, and it's going to go here. So it's going to look like this, plus 81, plus 81. Now, if I were to go factor this out, you don't have to do this, what I'm about to do, every time. I'm just showing that this works, okay? So 81 and negative 18. So two numbers that multiply and give me 81, but they'll add and give me negative 18. And if you do the math real quick, you find out it's negative 9 and negative 9, right? So isn't it a coincidence that that happens to be this number right here? So your takeaway is this. I can rewrite this as x, and whatever this number right here, the number that you're fixing to take the square of, minus 9 quantity squared, and then equals, right? You take your negative 56 plus 81. So 56 negative plus 81 is 25. Okay, so this right here is the process of completing the square. That's what it looks like. So from here, I've got to get the square from around this thing. So if you remember the inverse relationship, right? Square and square root. They're inverses of each other. So I'm going to take the square root of both sides. The square and square root are gone. I have x minus 9 equals a plus and minus 5. So from this, I'm going to make two equations. So it's going to look like this. I'm going to come over here. I'm going to have x minus 9 equals a positive 5, so the plus 5. And I'm going to have an x minus 9 equals a negative 5, the minus 5 there. So I'll add 9. So that's 14. I'm going to add 9 here. Oh, goodness. And that's going to be 4. And you're done. That's your root. That's your root. So that's the completing the square process. So I know that look makes you go, oh God, help us. I mean, that's a lot. But let me encourage you why this is a pretty handy method to know. Think of all of the methods thus far that I've shown you how to find the roots of a quadratic. There's been several of them, right? Like graphing, factoring, and in factoring, there's like several different methods of factoring for each one. Wouldn't it be nice to have one method you're like, okay, I can go to this method. So this method can be very beneficial to you to learn. I'm going to do another one where the a value is bigger than 1, so you can kind of see how do you wrestle with that. Okay, so give me a second. Let me just kind of reset some stuff here. And in fact, I'm going to try to find some that even have, yes, imaginary numbers. You know what? Hang on. Let me see real quick. Let me pull up my list here, and let me see if I can find a good, because I want to make this beneficial to you. So let me go up here. Let's see. Oh yeah. So let's see. I think this one would be a great one. So let me go to number 8. Yeah, that one right there. So this one can serve a few purposes for me here. There we go. So we have the benefit here that they've already moved the C value over for us. So thank you, whoever. The A value being 3, I'm going to go through and divide each part by 3. So that's going to give me an x squared. That's going to give me a negative 10x. Give myself a little space here. That would be 23. Okay? So where first step I'd have to move the C value over. That was done. Thank whoever. Second was divide by the A value. Check. Third part now becomes the whole completing the square, process thing here. So negative 10. So I got a half times a negative 10, which is a negative 5. Square it, and I get 25. That 25 will go here, and it'll go here. So it's going to be plus 25, plus 25. So from here, I can write it as x minus 5, right? Remember that number right there just goes here, squared, equals 48. So I'm going to have to take the square root now. So take the square root. X minus 5 equals, right now, square root of 48 is not a perfect square. So I'm going to have to do a little simplifying with this thing. So square root of 48. So the biggest perfect square goes into that. Let's see. My brain's shutting down. You know what? I'm just going to play. I think 16. 16 will go in that. Yeah. Duh. 16 and 3. Oh, goodness. All right, so square root of 16 is 4. Square root of 3. So square root of 48 simplified gives me a plus and minus for radical 3. Right? So now, this looks very daunting, but this is actually not, I mean, we're nearly done with this problem. So here's how you would write the answer in a situation like this. You'd write it just like that. So now the only difference here from these problems forward is you might have an I in it because it's imaginary. So like, for instance, if that had been like a negative 48, then you're going to pull an I, square root of negative 1 out, which is an I. So that would probably be the only new thing with this, but that's pretty much it. I'm going to let y'all try the rest of them and see how you do. So I'm going to stop it here, and happy studying.